Okay, welcome back to CE 529. And this is sort of the problem we were talking about. We have a 10-kilometer stretch of roadway. Share the whole screen, actually. We have a 10-kilometer stretch of roadway, which looks something like this. You have X naught is where we start. We have X naught where we start, and our demand is always 3,200 vehicles per hour, at least at the beginning. And the capacity, this 4,000 number was the capacity of these two lanes. And then we had a ramp at X3, that was always feeding in 400 vehicles per hour. And we said the demand is low enough that we are going to give that the priority. And based on that, we could figure out, okay, you have the 3,200 vehicles per hour capacity beyond this point. So only 3,200 can pass through. So when this 3,200 demand from X naught meets up with this 400 demand from the ramp at X3, the total demand here becomes 3,600. And now, because only 3,200 vehicles per hour can pass through, there is going to be a queue there. And what I wanted to show you was that this is what the queue is going to look like if you were to sort of analyze that. If you were to analyze the queue, I have that little sheet that I want to show you. You can analyze that queue with an input-output example problem. So what we'll do is we'll solve that little input-output problem. We are going to then estimate the delay like you are doing for, or you did already for the homework problem. Okay, we're going to estimate the delay. We're going to estimate the maximum queue length and all of that using the input-output method. But then we also want to apply what we call the Shockwave method. And for the Shockwave method, you're going to need something what we call the speed density relationships. You need to figure out what's going to be your speed density relationship for this situation. So I'm going to go ahead. Okay, so wait that in a second. And this is what your speed density relationship actually looks like. Okay, so you have density K, vehicles per lane kilometer on the x-axis, and then you have the flow rate, or sorry, this is flow density relationship, and you have the flow on the y-axis. And this is an interesting one because, sorry, folks. Okay, so this is a useful relationship for us. And if you look at the green shield model and all of that, the typical relationship between flow and density would have looked like something like this, like a parabolic shape. Okay, but we have a different model that is given to us for this particular segment of the roadway, which makes things somewhat easy in some ways, but maybe a little bit more challenging in some other ways. It does make it, at least the equations become simple. Okay, and so you could probably tell me, so what is the equation of this line right here? So if you want to write a flow density relationship for this line, what would that look like? What would that flow density relationship look like? You know the points, right? This is a QK diagram. So you have Q on the y-axis and K on the x-axis. And then you know this passes through 0. And then you can see that this point is, what is the coordinate of this point right here? If you want to write the XY coordinate of this point, 20 and 2000, right? So 20 on the X side and 2000 on the Y side. So this coordinate is 20 and 2000. So I'm going to write that down. So this coordinate is 20 and 2000. So can you, and then you know the other point, obviously, this, you know also that this is the 0, 0 point right here at the origin point. So you can write the equation of this line, right? That should be simple enough. Two lines. How does this sound? Q equal to 100 times K. How does this sound? Does this equation sound correct? Yeah. Okay, good. So you got a Q equal to 100 times K. So this means that your flow rate is always 100 times the density on the segment of the road. Okay. Now this is very interesting because now we are saying instead of a parabolic relationship, you have a linear relationship between flow and density. And based on this, you can probably also tell what is the average speed on this segment when you don't have congestion. So this equation represents the flow density relationship when you don't have congestion, but you should also be able to tell me the average speed on this segment without congestion. How do we find speed using a flow density relationship? Yeah.
You flow divided by the density.
Yeah, you just do flow divided by density. And because it's a linear model in flow density, okay, the speed is always going to be 100 kilometers per hour. Does that make sense? Because if you just kind of start to figure out what would Q divided by K look like for this, what does Q divided by K look like for this? It's just 100, always a constant. Okay. So what this is telling me is that I have a segment of the road where anytime I don't have congestion, the traffic moves at 100 kilometers per hour. Yeah, anytime I don't have congestion, which is not that unrealistic, by the way, because even if you look at, remember, if you recall the highway capacity manual diagrams, they also look something like this. So if I were to try to draw it, if you look at the highway capacity diagram, they also look something like this. So they also go straight for a long time and then they kind of drop at the end, right? So this is, so you could say that, you know, for the longest time, the speed actually remains at that constant value. So this is my, if you remember this curve, this looks like a speed. So on this side, on this curve, you have the speed, and on this side, you have the flow. So if you look at the highway capacity manual speed flow diagram, that also looks something like this. Okay. So this is good because then I can, you know, I can figure out, you know, my speed is always equal to 100 kilometers per hour in this example. Now, on the other side of this same chart, I have something even more interesting. And then this is this line right here. This is this line right here. Because this line actually represents the speed flow relationship in a congested situation, once the demand exceeds capacity. So this equation is for the situation where demand does not exceed capacity. That's your first line. And then on the right-hand side, I have my relationship with this orange line. It's when the demand does exceed capacity. Okay? So when the demand does exceed capacity, what does can you write down the equation of this line here too? So you can see that this jam density point is what? This jam density point is x-axis is equal to 100. What's the y-axis? What's the flow rate? 0, right? There's no flow at all. It's completely jammed up at that point. So 100 and 0 here is the point. And let's say, can you figure out this point right here as well? Can we figure out this point? Can you figure out this little point here? 40 and maybe 1500. Yeah, 40 and 1500 because this midpoint, so it's drawn to scale. So this point I'm going to call it 40 and 1500. I actually have an even better point. I can use this one too. This is 60 and 1000. So if I know that 2 points on a line, 60 and 1000, I can probably come up with the equation of this line too. Okay. Can you take a minute to write down the equation of this orange line based on these 2 points? 60 and 1000 and 100 and 0. So the 2 points that you're looking at are 60 and 1000 and 100 and 0. So 60 and 1000 and 100 and 0. He has the equation for me. 60 and 1000 and 100 and 0. Two lines. So you first need to find the slope of this line. Slope will be negative, right? So slope you can find by doing, remember the slope formula? Y2 minus Y1. So rise over run, right? X2 minus X1. Okay, negative 25 is very good. Yep. So now if I know the slope is negative 25, I could say the equation of the line will be Q equal to negative 25K plus a constant, right? MX plus B. That's how we do it. The y-axis is Q, negative 25 is the slope, x-axis is density, and a constant. And then I can plug in 100 0 point into this. I can plug in the 100 0 point into this. So that means C would be, if I plug in K equal to 0, or K equal to, or Q equal to 0, is the slope correct, right? Slope is correct, right? So 100 minus 60 is 40, yeah, 1000, yeah, that's correct. So I can say my equation will be Q equal to minus 25K plus 2500, is that right? And remember, one thing that we should note here, and I should highlight, is that this is vehicles per lane kilometer. Okay, so this is all per lane relationships. So the two equations I've come up with now, I should probably write down on the side here that my Q is equal to 100K for uncongested when I have no congestion. But then when I have congestion, it's going to be negative 25K plus 2500. And you can also tell me, and I can also tell you that there is the boundary here between congested and uncongested. We've simplified that. So when there is congestion, vehicles move at 100 kilometers per hour. And then when there is congestion, vehicles move at different speed. That will be determined by whatever the value of Q over K happens to be according to the second equation. Yes.
What's the 2500 from?
So 2500, I got it by trying to find this MX plus B situation in this one. So what I tried to do was I plugged in K equal to 100, 100, and Q equal to 0. So if I plug that in, I found the value of C, the constant in this equation, to be. So it's kind of like saying, what is my y-intercept essentially? So if you were to sort of extend this line over, it will intersect the y-axis at 2500. Okay, so that's kind of like writing the equation of this orange line. So this is the equation of this orange line. This first one, Q equal to 100K, is the equation of this black line. It's just trying to clarify where we got the 2500 from. Okay, so and then this situation is for congested regime. Okay. And this, remember, these relationships are per lane. Okay. So in the exam, I'll probably not give you the chart. I might give you the equation directly, because again, we have to work with like a 50-minute exam problem. So I'll probably give you, but it's a good way to kind of think about what does the congested versus uncongested situation look like. Okay. So now what I'm ready to do is go ahead and stop sharing this and pin this video. Okay. So what I'm ready to do now is take a look at the input-output problem, as well as the input-output problem and the Shockwave problem. Okay. So the input-output problem is rather simple here. The input-output problem looks like this. Okay. So for the input output problem, remember I told you guys that we draw a time and number of vehicles, vehicle count diagram. And remember, we draw this diagram at X3. So remember this, we are drawing this diagram. So this diagram is drawn at point X3. X3, which was our sort of like the top point that we had in our model, in our freeway. And then remember, we don't start at t equal to 0. Does anybody remember why there is this offset of 6 minutes? This offset is of 6 minutes. It's a 6-minute offset. Anybody recall why we have that offset? Yes, Dana.
It's because the traffic, like at the bottom, at like X1 has to drive.
Right. That's exactly right. So Dana says that, we started at X0 and there was no congestion. So everybody could just kind of get to X3, but it's a 10-kilometer stretch of the freeway and they're all driving at 100 kilometers an hour when there is no congestion. On average, it takes 6 minutes for vehicles to get to that X3 point. So our input output diagram, that's why start at t equal to 6 and starts at this point. And remember, this is all happening at X3. So at X3, my departure rate is only 3,200 vehicles per hour, right? My arrival rate is 3,600 because remember, 3,200 from the X0 that arrived and then 400 from the ramp. And remember one more thing. In this time window of t equal to 0 to 6 minutes, there will always be 400 vehicles per hour that will be passing. But why do I not have to analyze that piece? Why do I have to not worry about 400 vehicles per hour from the ramp that might actually be passing this location, X3, between t equal to 0 to 6 minutes? Why do I not have to worry about that? I'm not drawing them in the diagram, in the queue. I'm not interested in them. Can you guess why? 400 vehicles per hour that pass through from the ramp and cross X3. Because 400 vehicles per hour is much lower than the capacity. My capacity is 3,200. Vehicles that can pass through X3 is 3,200 vehicles per hour. So if my demand is only 400, there will be no queue. And if there is no queue, I don't care, right? I mean, I'm not interested in that situation. I'm only interested in when there is a problem that develops. And that problem starts at t equal to 6 when the demand from X0 that now reached X3 combines with the demand from the ramp that was 400. And if you recall that, I'm going to quickly show you, this is what that looked like, right? So 400 plus 3,200 demand from the bottom, it catches up and gets me to that 3,600 demand. Okay. So now the input output problem is rather simple, actually, if you think about it. So, and we have solved this type of problem before. So 3,600 vehicles per hour. Okay. That's your demand coming in. I don't know if I can. But I think that's okay because I think we will be able to read it. And then it looks like my capacity is always 3,200. So my supply or my output curve or my output diagram always has a constant slope of 3,200 vehicles per hour. And we can convert that into vehicles per minute because my time axis is going to be in minutes. Okay. And then my demand axis is 3,600. My arrival curve is 3,600 vehicles per hour. What happens to this curve at t equal to 21? Remember, we did specify that demand level for our problem was, if you go back and take a look at this problem, my demand reduces to 2,000 vehicles per hour at t equal to 15 minutes. My demand reduces to 2,000 vehicles per hour at t equal to 15 minutes, but that happens at X0. Okay, so my total demand reduces to 2,400 vehicles per hour at t greater than 21. And I think this is something that we had specified the other day, right? We had specified that the other day, that this is what's going to happen. So at t equal to 21, what happens? Slope of my arrival curve changes. At t equal to 21, if you sort of plug that in, t equal to 21, the slope of the arrival curve changes to only 2,400 vehicles per hour. Okay. And then because now the departure curve is steeper, the departure curve catches up or with the arrival curve, because arrival curve has now become a little bit less sloping. And at this point, the Q dissipates. Now let's figure out what time actually does the Q dissipate. Okay, so again, we can do the same exact things that we had been doing before, is to write down the equation of the arrival curve, write down the equation of the departure curve, write down number of arrival, write down number of departures, and then we can derive our total Q. When does the Q dissipate? Okay, so the Q will dissipate. So first of all, what's going to be the length of the maximum Q? Okay, so if we take that approach that we are taking for our homework and solve this problem, we figure out that t equal to 28.5 minutes is when the Q completely dissipates. Okay, and we can take a quick minute to solve this problem too, and then we can write down what the arrival equations were and what the departure equations were very quickly, and then you all can solve it. Okay, so I'm going to try to do that a little bit here. Okay. So if you recall this from our discussion, our arrival rate was 60 vehicles per minute for T being 6:21, and then it reduces to 40 vehicles per minute at T greater than 21. Okay, at T greater than 21, sorry. Okay, T greater than 21. And then we have the departure rate is always 53.33 vehicles per minute at all values of T. Okay, at all values of T, my departure rate is always this. Okay, and we had that discussion the last time. Now, it's pretty easy if you want to write the arrival equation, number of arrivals equation. Probably should switch back here. So I want to pen, and then I want to share a screen here. Share the whole screen. Okay. So if I want to now write down my number of arrivals will always be it's always going to be 60 times T. And then you can do 60 times T minus 6. If you always want to keep your scale same, you can start off with number of arrivals being 60 times T minus 6. Okay. And then this rate continues for 21 minutes or up to 21 minutes. So this is the value of T6 T greater than 6 and up to T equal to 21. And then once you have hit, it will be 900 plus 40 times T minus 21. Okay, now I want you to ask here, do these equations make sense? It's very important that these equations make sense to you. If they don't, please let me know. Okay, so I'm going to take a little pause here. Recording. So number of departure equation was fairly simple, but 53.33 times T minus 6, because again, I'm offsetting everything by 6 minutes, 900 plus 40 times T minus 21. Okay, so this, I should probably correct this too. Okay. Now, can we quickly, somebody calculate this for me and verify what we get out of this? So this, you solve this for T, you get the time at which number of arrivals at X3 become equal to number of departures at X3. Okay, and that's the time when the Q goes away. Can we please verify what happens with this? Solve for T for me, please. If you were to solve this equation, you get t equal to 28.5. And that's going to be your time of t equal to 28 minutes will be when the Q goes away. Time at which Q dissipates. Now, next question is, what is the maximum length of the Q at x3? What's the maximum length of the Q at x3? Maximum length of the Q is easy to identify. It's whatever is the Q length at what time? Whatever is the Q length at t equal to 21, right? Because that's when the departure rate sort of changes. I mean, arrival rate changes and starts to dissipate the Q. So max Q at t equal to 21, that's easy to get. You basically subtract arrivals minus departures. If you do that, so if you plug in t equal to 21 here, it's 900. And then if you plug in t equal to 21 here, it's going to be 21 times 51.33. It's going to be 1,000, I think. So arrival minus departure, it will be equal to total arrivals would be, no, it's going to be 800. At t equal to 21. Is that 53.33? Yeah. So 21 minus 6 is 15. 15 times. Yes, please.
So are you running 21 into the first one?
Either one is fine because it's going to be the same thing, because at 21 is sort of my break point. So both equations give me the same number. But I'm thinking I'll plugging in the first one. Yeah. But even if you plug in the second one, t equal to 21 should apply, and 21 is 0. So this whole thing goes to 0. So you're basically okay. So anyway, number of arrivals will be 900 minus number of departures. If you plug in 53.33 times 21 minus 6, that gives you 15. And I know that will be about 800. So you get the maximum Q of 100 vehicles. Okay. Remember this number. Yes, please.
Would we want to say vehicles per lane, or is this just vehicles?
This is total number of vehicles right now, because arrival and departure, this was the flow rate that was given to us. That was the total flow rate. So the question was, do we want to say 100 vehicles per lane, or is it 100 vehicles total in Q? So my understanding, the way they specify this is the total arrival rates and total departure rates. Okay. So when they specify the capacities for the whole freeway lane. So that's why this is the 100 vehicles is the total Q length right now. Okay. So not per lane, but 100 vehicles of total Q length. So remember this number though. We will come back to this after we have done the Shockwave analysis. It's going to be interesting. Yes.
So are we assuming that the flow is the same after X3, because you just like saw that chart where after congestion the flow changes?
Right. So after congestion, the flow changes with density. That's a great point. But that's the thing. The input-output method doesn't take into account what's happening on the segment of the highway. Okay. So input-output method just thinks of Qs as they arrive at X3. Okay. So it always looks at what's happening at X3. I'm just not going to worry about what are the flow, density, and speed implications of this are. I'm just going to go ahead and analyze my Q as if they're all sort of magically appearing at X3. And actually, this is the great point of the paper that I'm going to show you in a little bit. So this is sort of the assumption that the X3 makes. So I'm going to go ahead and pin this here. Stop sharing and pin that. So this is sort of the way that input-output method analyzes the Q. It's assumed that all of these vehicles, as they arrive, they just stack up at X3, which is obviously not the case. They don't go ahead and stack up at X3 and then do a first in, first out as they leave the congestion. Okay. But obviously, input-output method is a very simple method to analyze. It doesn't make sense from this perspective because obviously queues of vehicles doesn't just go stack up vertically. It doesn't. We know that. So it's missing something. But what it's missing, that's the whole point of this paper, is that what it's missing is just one of those elements of the queue that you cannot quite capture with the input-output method. But as you will see, that we'll be able to correctly capture the Q dissipation time when the Q goes away. It will be the same regardless of whether you're using Shockwave method or the input-output method. So this is a great question as to what happens to, we know that the speed will slow down once there is congestion. And it looks like that input-output method doesn't account for that. That is right. But because it assumes a vertical stack queue, it also assumes wrong about how many vehicles are in the queue as well. So you'll see that there is going to be certain things that are going to come out different, but there's going to be certain things that come out the same. And computationally, this approach is way simpler to estimate. Okay. So then one more thing about this is that you could also, if you want to find out the total delay that is being caused by the input-output method, like, all of this, the total delay is fairly simple as well, is that you just kind of get this very small shaded area. You take this and you just get the area under this curve. And if you estimate the area under this curve, that estimates what we call the total delay. So this is essentially a triangle shape. So if you get the base times height, you can get the total delay. And then the total delay is going to be, we know that the max Q is 100 vehicles per hour, or 100 vehicles is the max Q length. That's right here, right? The vertical gives you the Q length. And then you can think of this as a height going this way. And then the height going this way kind of gives you the area of the total triangle. So if you do half times 100 vehicles, the base, times 28.5 minus 6, basically that adds up this whole height. Okay, this whole base here. Okay, you can estimate the area of this triangle. And then if you convert that into vehicle hours, you'll be able to get 18.75 vehicle hours of total delay. Okay, so total delay is area of this triangle that you can see here. And if you were to solve it, it's going to be just boiled down to half times 100 times 28.5 minus 6. Okay, and you can verify this, that this is going to be the area of this triangle. Okay, so I'll just kind of assume, and if you need help with that, I can try to help you in the lab. But let's first assume for a second that this is the correct value for total delay, which is 18.75 vehicle hours. Okay, vehicle hours. So I'm basically taking this number, half times 100 times 28.5 minus 6, and then dividing that by 60 to get like a reasonable looking number in terms of vehicle hours. So if you want to estimate that in vehicle minutes, it's going to be just this number times 60. Okay? So now let's think about what's actually happening on the freeway. As this congestion develops, what is the picture, the real picture on the freeway? This is a good sort of theoretical estimate. As I said, I can get the total delay at X3. I can have all of this lined up. That's wonderful. My problem, though, is this obviously does not represent what happens on the freeway. It does not represent that speed reduction that you'll experience. You will not be able to arrive at X3 at 100 kilometers an hour. Not everybody would be able to, because they are going to run into the congestion that's spilling back from X3. So there is going to be a shock wave now, right? So now, to analyze the shock wave, we draw what we call a time-space diagram. And we draw a time-space diagram, and we draw it right below. So this paper does a very good job of drawing it right below the input-output Q diagram. And then this is what's happening. You have the time on the x-axis. You have the location now at the y-axis. So remember, the key difference between those two charts, on the first chart, we had the vehicle counts on the x-axis, y-axis rather. Now we have location on the y-axis, so different things. Okay? And then you have what's going to happen at these different locations. So these broken lines represent the traffic flow that is able to make traverse through the freeway at free flow speed. Okay, so you can see, can you tell me what do you think will be, if this is X kilometers on the y-axis and this is time in minutes, you could probably tell me what is going to be the slope of this broken line. Okay, this represents the flow that goes from X0 to X3 at 100 kilometers per hour, and it reaches there at what time? So if I were to project this down or up rather, you could do either one. You could do project it because these two diagrams have the same x-axis and the same scale on the x-axis. This was t equal to 6 minutes. So if you were to project it down, this is also going to be t equal to 6 minutes, right? Make sense? Now, if you were to, and then at t equal to 6 minutes, what's going to happen? There's going to be a bottleneck that's going to create congestion at x3. And now remember that picture where we showed you that video where the shock wave was separating the boundary between congested and uncongested regimes. So that's exact thing that's going to happen here. And there is going to be a boundary moving backwards. And we don't know yet whether it's going to be moving backwards or not. But I mean, I know it because I've solved this problem, but you don't know yet. But you know that the flow rate on one side of that boundary will only be 3,200. How do I know that on the congested side, the flow rate is only going to be 3,200? On one side of the boundary, the flow will only be 3,200. How do I know that? Oh, actually, and one more thing. So in the problem, I don't know if I said x3, the ramp it is x3. The ramp actually is at x1, sorry. The ramp is located at x1. I don't know if I said x3. The ramp is actually located at x1 rather. Okay, so please locate the ramp at x1. If I said it x3, please, my apologies. The ramp is located at x1, and that's why you'll see that at x1, the flow rate changes from 3,200, the original demand, to 3,600. And then when that 3,600 hits here, there's going to be a shock wave formation. I know one side of that shock wave will be the congested condition where the flow rate is only 3,200. Why am I reducing this flow rate to 3,200? That's exactly right. That's the bottleneck capacity. Only 3,200 vehicles per hour can pass through X3. Yes.
So I'm just curious, like when it gets really congested, like thinking about kind of freeway when cars are bumper to bumper, is the flow rate, like, is that the capacity flow rate when that's happening?
No. Bumper to bumper is basically, bumper to bumper would represent this part of the curve. So if you look at like in terms of the curves, the bumper to bumper situation would represent sort of this part of the curve right here, the bottom part. Now you're at bumper to bumper. The capacity part of the curve is usually here. It's very unstable in nature. So that's the problem with capacity. It's problem and an opportunity both in some ways, right? It's a problem because once you enter that close to capacity regime, things could fall apart really, really badly, really quickly. But on the flip side is, if you can actually even take away a little bit of the flow, okay, you could be in smooth sailing regime, right? So this capacity regime is very unstable. The problem with that is adding even a little bit could cause a lot of problems, but even taking away a little bit could solve a lot of problems too. Okay, so yes.
And so when a queue develops, that doesn't mean like bumper. When I'm imagining a queue, I imagine like cars are literally stacking up.
Right. So no, queue could be just like everybody's slowing down somewhat. So they're not just able to move at 100 kilometers per hour. Their free flow speed as they were going before. So when I say queue in this problem, doesn't necessarily mean it's completely bumper to bumper, no movement at all. It's just a matter of you have some movement once the queue has already developed, and then the vehicles are moving slowly. But behind the queue, vehicles are moving fast at their original speed of 100 kilometers per hour. That's what's happening in this problem. Okay, I hope that clarifies. So now I need to figure out that, okay, I know that once I hit this point, my flow rate is only going to be 3,200 because that's the bottleneck capacity. But what's happening on the other side, for the folks who haven't yet hit the congestion, what speed are they moving? They're moving at 100 kilometers per hour. Capacity of that segment is 4,000. So anytime we have total demand in this segment that exceeds or that is less than 4,000, everybody can move at 100 kilometers an hour. It's only when they hit this X3 where the capacity is only 3,200. That's when the problem comes. But this is very interesting because I know the flow rate. This is the flow rate X naught plus the flow that comes from the ramp. I got 3,600 over here. That's wonderful because it's less than 4,000. So everybody can move at 100 kilometers an hour. Now, I want to find speed of this shock wave. Okay, I want to find this shock wave that separates the regime with this 3,200 flow and this 3,600 flow. I want to find the speed of that shock wave. How do I get that? We remember we derived the equation for the shock wave, right? We derived the equation for the shock wave. UW is, if you recall that, Q2 minus Q1 over K2 minus K1. So if I know the two regimes, I can find the speed at which the boundary between them moves. Okay. Do I know Q2 and Q1 in this equation? I know that, so I can assign, or rather, if I want to write that in their terminology, I would say in this speed of this shock wave, I can write it as, okay, bear with me here, QC minus QA2 divided by KC minus KA2, right? So I'm basically using their terms for what they're calling these different regimes. So they're calling this congestion regime C, and then they're calling this A2, B2, A1, B1. And they separate it by the ramp because, you know, the density would be the same at that point. But we'll talk about that. But right now, you're just trying to find the boundary that separates, the speed of the boundary that separates A2 and C. It's going to be QC minus QA2 over KC minus KA2. So what do we know about these? So basically, this will help us find the slope of this line. Do we know QC? Do we know QC? The flow rate in the regime C, right? It's 3,200. We know that. Do we know QA2? You know QA2 as well, right? It's 3,600. Make sense? Okay. Do we know KC though? This is where it gets a little bit interesting. Do we know KC? And do we know KA2? Do we know density of this regime and the density of this regime? Okay, so I want to find this KC and KA2 that I don't know yet. And remember, this is the Shockwave speed formula I'm applying. So this is the Shockwave speed formula. I just need to figure out what is KC and KA2. Let's first think about KA2. Do we have a means of, so first of all, A2, is this congested regime or uncongested regime? A2, uncongested, right? Because my demand does not yet exceed capacity at this point. So A2 is uncongested. Do we have an equation that relates flow and density in the uncongested regime? We do actually have that because remember, we operationalize these equations from this chart that they had given us. The only problem with this chart is that they messed with us a little bit, is that they gave us these per lane relationships. These densities are per lane right now. But it's okay. We can convert because we know this segment has 2 lanes. We can convert our flow rates and densities into per lane relationships. And then when we go ahead and write down to apply our Shockwave equation, we can convert them back to 2 lanes. Okay. So what did we say about this equation? We did come up with this equation, right? We know that the uncongested regime, Q was equal to 100K, right? And then for this equation, we came up with Q was equal to, what was that? Minus 25K plus 2,500. Remember that? But again, remember, this is per lane though. Now, which equation would you apply to regime C? Which equation would you apply to regime A2? That's the question. Which equation would you apply to regime C? And which equation would you apply to regime A2? Okay, I'm going to give you some answer. So I'm going to apply this equation to regime A2 and this equation to regime C. That makes sense, right? Because C is the congested regime, A2 was the uncongested regime. So that's what I'm going to do. But remember, these are per lane. So that's what we have to be careful about, is that make sure that our application is per lane. So I think we have run out of time right now. So I'm going to stop here and we'll pick this discussion up back. Maybe we can spend some time in the lab to at least wrap up this while this is still fresh in our mind. So you can work on your homework problem as well. So maybe we'll take 10 minutes in the lab to go over this. Okay. All right. Thank you. We'll pick this back up in the lab.